So, obviously, we're doing class remotely because campus is closed. Sorry, the announcement about that didn't happen any earlier, but that is the fault of CCSJ for not making their decision until this morning. I wish they'd made the decision last night. If they had committed last night, I would have sent out the announcement last night, but I sent it out as soon as I heard from CCSJ that the campus was closed. So, um, we're starting up chapter 17. We just finished chapter 16. So, chapter 17 is on the various smaller bodies throughout the solar system. The chapter 16 homework is due on the 14th. The chapter 16 quiz will be on the 12th. That is this Wednesday. Um, the chapter 17 homework is due on the 21st. And the lab we were supposed to have today will be delayed until next week. And then the last lab will be pushed back another week. Um, in general, people have been okay about getting their labs done, so there's room for that. We'll just push the labs back a little bit. Okay. So, chapter 17 on moons and smaller solar system bodies. So, we will describe the relationship between the moon's movement and the month on Earth. We'll talk about the surface features of the moon. We'll differentiate between highlands, maria, and craters on the moon. We'll talk about the effects of the moon's orbital period on the ability to see only one side of the moon from the Earth. We'll describe the phases of the moon. We'll describe the conditions necessary for a solar eclipse to occur. And we'll differentiate between the umbra and the penumbra. We'll talk about the necessary conditions for a lunar eclipse to occur. We'll discuss how the moon's orbit about the Earth causes tides. We'll name the terrestrial planets that have moons. That's pretty easy. We'll compare the number of moons for the Jovian planets to the number orbiting terrestrial planets. We'll describe some of the key features of the Jovian moons. We'll talk about the unusual orbit of Pluto's moon Charon. We'll differentiate between meteors and meteorites. We'll talk about the asteroid belt uh, and the composition and behavior of comets. So moons are natural satellites. Um, More than 250 are known at present. It's I think it's more than 350 at this point. Uh, though I'm not, I'll just leave it at that. The numbers went up recently. Many are small, less than a kilometer in diameter, and a small number are large. Um, and there are other objects like comets, asteroids, interplanetary dust. These are some of the other objects that are orbiting the sun. So our moon uh, is uh, large, and then we first landed on the moon on July 20th, 1969. One of the nice things that was put on the moon by one of the later missions to the moon was a retroreflector, which is basically it's a it's the corners of a cube, a bunch of corners of a cube lined with mirrors, and they reflect. They're designed so that if you shine light on them, they reflect light back in the exact direction it came from. And this was there to reflect laser beams from Earth, so we can measure a number of things using these retroreflectors. We can measure the rate of continental drift on Earth, changes in the Earth's tilt, the distance to the moon, and the gravitational constant, among other things. The average distance to the moon is Uh, 3,000, 384,000 kilometers or 240,000 miles. And there's an image of the moon. Oops. It is the second brightest object in the sky after the sun. And the origin of the word is not known. Um, uh, but there are many primitive and modern societies base their religious ceremonies on the cycle of the moon. It's just one of the basic things we base calendars around. The two major cycles are the cycle of the sun, the seasons for the year related to our orbit around the sun, and the months tied to the orbit of the moon around the Earth. So our month is based on the moon cycle. Lots of religious ceremonies are based on the cycles of the moon. Um, like the timing of Easter has to do with the interactions of the moon and the solstices. And in a weird coincidence, it seems to be a coincidence. There does not seem to be actually any evidence that these are actually tied together. The human ovarian cycle is also very close to the 29 and a half day lunar cycle. Um, but it doesn't seem to have be that there's a causal connection. Um, there's a lot of debate about that one. Our moon is the largest moon of any of the terrestrial planets, Mercury, Venus, Earth, and Mars, by a lot. It's the fifth biggest moon in the solar system. Um, and all the bigger ones are orbiting the Jovian planets. Um, I mean, like it's weirdly big. It's one of the phenomena that needs one of the big exceptions that needs to be explained by models of our solar system is how Earth got so big a moon. One complete revolution takes around 29 and a half days. Uh, and it rotates on its axis at approximately the same rate. Therefore, we only see one side of the moon. So basically, the moon is rotating at the same rate that it is revolving around the Earth. So the same side of the moon is always facing us. If you were on the moon, because the moon rotates every 29 and a half days, the sun would appear to rise and set every 29 and a half days. And the surface features of the moon formed millions of years ago without erosion to erase them. So there's very slight erosion on the moon from meteorite impacts, but it's very slow, and stuff millions of years ago is still quite clear and sharp. What's going on? Where is my mouse? Okay. What's going on? There we go. Come on. There we go. So this is an animation showing the orbit of the moon around the Earth. You can see how the same side of the moon is always facing the Earth because it rotates at the same rate that it revolves. So the whole moon gets illuminated at different times. So there's not like a dark side of the moon. There is a far side of it. The same side always faces Earth. So the moon is nearly spherical. It has a diameter of 3,476 kilometers or 2,160 miles, which is about a quarter of the diameter of Earth. And its mass is about an 81st of that of the moon. The lower mass and lower diameter combine to give it lower gravity of around a sixth of the gravity on Earth. The lower mass makes the gravity less, the lower diameter makes it more, but the combination makes it about a sixth. The average density is about 3.3 grams per cubic centimeter as opposed to the Earth's 5.5. It's less dense than the Earth. Its density matches more or less the density of the mantle. The surface gravity is only a sixth of that of Earth's. Therefore, your weight on the moon would be a sixth of what it is on Earth. So if you weighed 150 pounds on the moon, you would only weigh 25. And the average reflectance, albedo, is only 7%. So only 7% of the light that is received from the sun is reflected. The moon is actually quite dark. It's a quite dark gray, but against the background of the blackness of space, it seems very bright because it's putting out a lot more light than anything else. Now, we know some things about the history of the moon. Using radiometric dating techniques, we've been able to date the rocks on the moon that we brought back from landing on the moon. The mountain rocks are around 4.4 to 3.9 billion years old. They're significantly older, while the rocks in the plains are 3.9 to 3.1 billion years old. And in general, no rocks older than 4.4 billion or younger than 3.1 billion years old have been found. So we think the moon is around 4.4, 4.5 billion years old. So no rocks older than 4.4 billion makes sense. And younger than 3.1 billion years old is because there just hasn't been any activity on the moon for the last several billion years to make new rocks. There's no, all the volcanic activity, all the et cetera has ended. Now, if we look at the inside, from the inside to the surface, there's inner core, which is iron-rich and solid, an outer core, which is iron-rich and maybe semi-liquid, a rocky mantle, a crust, and a regolith, which is like a powdery material, like powdery dust covering the surface, pulverized dust and rock from all the meteorite impacts. The thickness of the crust varies across the surface. It presently does not have a magnetic field, so the core is not very active. But rocks brought back show some magnetism, indicating that the moon had a slight magnetic field in the past. So 3 billion years ago, it might have had a magnetic field. So here's a video about some of the characteristics of the moon. Give this a second. Come on. Okay.
Over 150 moons orbit the solar system's planets, and one of those moons calls Earth home. The moon was formed about 4.5 billion years ago, when, according to one theory, the Earth slammed into another early planet. Debris from this collision began to orbit Earth and accumulated, forming today's moon. The Moon is the fifth largest natural satellite in the solar system, with a diameter just under the width of China. It's composed of an iron-rich core, plus a mantle and crust containing minerals made of magnesium, oxygen, and silicon. The Moon's surface was once geologically active and covered in an ocean of magma. But today, apart from traces of water ice, the surface is completely covered in dust and rocky debris. Countless craters dot the Moon's surface, each formed by objects such as meteoroids, comets, and asteroids crashing onto the Moon. The largest crater, the South Pole Aitken Basin, spans across a quarter of the Moon's surface and is nearly deep enough to fit Mount Everest inside. The Moon orbits our planet at an average distance of 30 Earths. It rotates at the same rate that it revolves. So as it revolves around our planet, the same side of the Moon faces the Earth at all times. From the Earth's surface, we can observe 8 distinct, traditionally recognized stages of the Moon's illumination. Called lunar phases, they have been observed for thousands of years and even provided the basis for the earliest calendars. For most of human history, the Moon could only be studied from afar. But on July 20th, 1969, humans were able to close that distance with the American spaceflight mission Apollo 11.
That's one small step for man, one giant leap for mankind.
It placed humans on the Moon for the very first time, bringing our understanding of Earth's only natural satellite one step closer.
So the most widely accepted theory of the Moon is the Great Impact Theory, where a planetized object, something about the size of Mars, struck the Earth with a glancing blow around 4.4 billion years ago, resulting in the ejection of matter into orbit to form the Moon, and leading to the creation of the Moon. So a bunch of the material flew off, a bunch of the material fell back down onto Earth, and a large lump of it condensed to form the Moon. And that explains why the Moon has properties similar to the mantle, because it's basically made from material that was knocked off the surface. You know, the upper layers of the Earth didn't dig out of the core. And that's but it does have isotope ratios very similar to rocks on Earth. Let's see if this works, or if these are just okay. Thought I'd gotten these working last night, but apparently they are broken.
Take the next step in treating your moderate to severe
And this is why
ulcerative
I
colitis
wanted
with
to have them
Entyvio,
working,
the
because I
only
don't
gut.
want stupid ads. So this is an animation showing that information. We had, another planet-sized object struck the Earth. So this is known as the giant impact theory, where two planets collide, and the composition of the lunar mantle and crust is similar to Earth's mantle. Some prominent features of the moon are, other than the very obvious phases of the moon, some of the most prominent features include craters, basins, plains, um, rays, rills, mountains, and faults. A crater is a Greek term for bowl-shaped, and lunar craters vary from large to small, and they're generally believed to be formed by meteorite impacts of various sorts. And for individual craters, the volume of the rim and the crater are about equal, because that's just the material that got ejected out. So the surface of the moon, there are the highlands, which are the light colored part of the surface. This covers about 85% of the surface. And they extend several kilometers above the lunar surface. They're a form of the older lunar crust. Um, there are also lunar plains. These are also called maria, Latin for seas. These are these large, darker areas on the moon that are believed to be craters formed by a meteorite impact that caused cracking, which then flooded with volcanic lava. They're dark in appearance because these are flat playing areas are covered in basalt, which is darker and reflects even less light than the average surface area of the moon. They were called seas because people saw these dark areas and first thought, oh, those look like bodies of water. Um, and the surface of the moon is covered by a layer of loose debris called regolith, which are fragments of material from various meteorite impacts. And the rock samples we've examined from the moon are very similar to volcanic rocks on Earth. So the plains were produced by volcanic eruptions and the resulting enormous lava flows. There are volcanoes in a few places, extinct volcanoes in a few places on the moon we can see as well. And apparently the moon's interior was hot enough to cause these major eruptions from around 3.9 to 3.1 billion years ago. And they seem to have been triggered mostly by major meteor impacts. You get a really big crater, and in that process, it cracks the crust beneath it, leading to where lava can flow up and flood these craters. Uh, and there were flow of enormous amounts of lava. So craters and basins are the best known features on the moon's surface. They come from the Greek word for bowl. About 30,000 can be seen using an Earth-based telescope. And the craters on the moon range in size from literally microscopic. We brought back materials from the moon where we have little round droplets formed from an impact that have tiny impact craters on them, to hundreds of kilometers in diameter, to enormous, massive in size. And the shapes of the craters change with their diameter. Up to about a kilometer, they're smooth, bowl-shaped interiors. Greater than about a kilometer, the interior gets flat. And much greater than a kilometer, you have a flat floor with a central peak where the ground bounced up after the impact. Most of the craters were formed between about 4.4 and 3.9 billion years ago, when there were a lot more impacts, a lot more meteorites, a lot more junk flying around in the solar system. But most of that material hit stuff and thus got cleared out. So there were a lot less impacts later than that. After about 3.1 billion years ago, the moon cooled down enough that molten rock could no longer get to the surface, and it appears to have been geologically quiet for the past 3.1 billion years ago or so. There are still some, quakes. There are moonquakes, but they aren't very common, and they're small. So here are some craters on the moon. Rays are streaks that extend outward from some of the craters. They're thought to be pulverized rock that was thrown out when the crater formed. And these rays are brighter. They reflect more light than the crater because powdered rock reflects more light than just regular rock. Um, uh, and occasionally the ray systems are also marked by secondary craters formed from flying debris flown from the primary crater. So you get a really big impact, sometimes really big rock gets flung up, comes back down, creates a secondary crater. Rills are long, narrow trenches or valleys. Some are straight, some are curved. They're thought to represent a separation or crack caused by moonquakes. They're similar to the ones known to form from earthquakes. And we know there are moonquakes still, but they aren't very big anymore. And the mountain ranges on the moon can be as high as 6,100 meters. They all appear to be formed in a circular pattern bordering the lunar plains. Therefore, they probably weren't formed by the same processes that form mountain ranges on Earth, especially because the main processes that form mountain ranges on Earth involve tectonic plates, which the moon does not have. And there are faults, or breaks or fractures in the surface of the moon along which movement has occurred. They result from the movement of the moon's crust along that break. And since there's little or no erosion on the moon, the difference in elevation caused by these faults remains for millions of years. Basically, if you have something that can cause a shift with a fault, along a fault, that is never going to that's going to stick around for a very long time. It's not going to get easily worn away. So here is a video about the surface features of the moon. Come on, load. There we go. So this is a tour of the moon from the Lunar Reconnaissance Orbiter.
To nearly everyone, the moon appears to be a sterile, gray, unchanging world. But while the moon has remained largely unchanged during human history, our own understanding of it has evolved dramatically. Thanks to new observations, we now have not only unprecedented views of its surface, but a whole new tour of the moon that shows how both it and other rocky planets in our solar system have been shaped over billions of years. We'll start with one of the largest impacts, Oriental Basin, a feature that's as wide as the distance from New York City to Cincinnati. Using new elevation measurements, we can clearly see the effects of what is likely the last giant impact event in lunar history, with its outer mountain rings rising many kilometers above the lowest points inside the crater. The interiors of some craters in the moon's polar regions, like Shackleton, haven't seen sunlight in over 2 billion years. However, new measurements have created our best yet maps of these types of craters, allowing us to see deep into the shadows of this surprisingly young-looking impact crater in the south that's more than twice as deep as the Grand Canyon. Some impacts are invisible for other reasons. Although the ancient South Pole Aitken Basin is difficult to see from orbit because it is so large, new LRO topography maps reveal the largest impact basin in the Earth-Moon system, measuring several kilometers in depth and around 2,500 kilometers in diameter. Only the Hellas Basin on Mars rivals it in size. One of the youngest large-scale impacts on the Moon is the Tycho crater. This fresh crater may have formed only 108 million years ago, when dinosaurs roamed the Earth. We now also have an extreme close-up view of the crater's central peak, revealing a mountain with sharp edges, building-sized rocks, and a central boulder about the size of a baseball stadium. The Aristarchus Plateau is another recent lunar formation that has long interested scientists and astronomers. The crater itself formed in the same era as the Tycho crater, and what appear to be snaking river valleys were actually carved by ancient lava flows. Next, we arrive at Mare Serenitatis on the near side of the Moon. In December of 1972, the crew of Apollo 17 landed in the Taurus Littrow Valley, marking the last time humans have visited the surface of the Moon. With images from LRO's narrow-angle camera, we can clearly see the evidence of that visit. In this image, you can easily see the base of the lunar lander, along with the lunar rover, parked far from the blastoff zone. You can also clearly see the astronaut trails and the wheel tracks left on the lunar surface. We now head to the far side of the Moon, which cannot be seen from Earth. Our first stop is the Compton-Belkovich region, which shows evidence for young volcanic activity in the far side highlands. This feature is unique not only because it is isolated from other volcanoes in the area, but also because it is located nowhere near the Maria, where volcanoes are usually found. Also, on the far side we find the Jackson crater, which, like the Tycho crater on the near side, has an extensive and complex ray system. In fact, this crater is often considered to be like a twin to Tycho. Finally, the Tsiolkovsky crater stands out as an excellent example of a far-side crater filled with a sea of ancient lava, known as a mare. It is particularly interesting to scientists and other observers because of its isolation from other similar craters, as well as its beautiful central peak. As we continue to study the Moon, our understanding of it improves, giving us new insights not only into how it has evolved over time, but also how other rocky planets in our solar system have come to look the way they do. With new missions, new instruments, and new technologies, we will continue to improve our knowledge of the Moon and better understand the history of our solar system.
So the moon's orbit around the Earth is not in the same plane as the Earth's orbit around the sun. It's tilted by about 5 degrees. And because of this tilt, there's actually a few interesting effects that occur. It's possible for the moon to be directly overhead at any latitude from 28.5 degrees north to 28.5 degrees south, depending on a variety of factors. And both the rotation of the moon on its axis and the moon's revolution around the Earth are counterclockwise from a North Pole perspective. That's expected. It's rotating like everything else in the solar system. But this tilt means that the shadow of the moon will only hit the Earth some months. And that's an eclipse. So the tilt of the moon's orbit is why we only have about 2 solar and 2 lunar eclipses a year. So this is, an animation showing how we don't have a solar eclipse every year. So if the orbit wasn't tilted, we would have one every year. But because it is tilted, sometimes the shadow is too high, and sometimes the shadow is too low. But sometimes, about twice a year, the orbit is aligned such that you get a shadow on the Earth. And you get eclipses. So there's the orbit of the Earth around the sun, there's the orbit of the moon around the Earth, and there's about a 5-degree angle there. So the moon orbits the Earth in an elliptical orbit. It's pretty close to circular, but it is still elliptical. The synodic month is the month we see. That's the cycle of the phases. That occurs every 29 and a half days. It's the basis of most ancient calendars. It's the basis of the first Roman calendar, for example. It's the apparent period of the moon's revolution around the Earth. Now, if you trace the revolution, but much like there is a sidereal day and a solar day, there's a sidereal month and a solar month. There's a sidereal month and a synodic month. The sidereal month is the true period. So the reason the synodic month is longer than the actual time it takes the moon to complete one circle is because the Earth travels around the sun. So the moon has to travel a bit further to catch up. And that's a couple of extra days. So the true period of the moon's revolution around the Earth is over 27.3 days. That's the sidereal month. And that's caused by the orbit of the moon around, the orbit of the Earth around the sun. Now, the difference in 2 days between the sidereal and the synodic month is due to the fact that the Earth-Moon system is also moving around the sun. So as it cycles around the sun, the moon has to travel a little further to be in the same relationship between the sun and the Earth. The moon is tidally locked by the force of Earth's gravity over geologic time. Basically, the rotation of the moon slowed down until the period of its rotation and the period of its revolution around the Earth are the same. This causes the same lunar hemisphere to face the Earth. This is caused by tidal forces. The difference in strength on one side of gravity between the near and far sides works to slow rotation and try and make one side always face the Earth. The moon is actually doing the same thing to the Earth, but it's happening much slower because the Earth is much bigger. But it causes the same lunar hemisphere to always face the Earth. So here's an illustration showing the difference between the sidereal month and a synodic month. To a distant star, over after 23 7 1/3 days, it lines up back to that star. It's completed one complete rotation, but to line up with the sun again, it needs to travel another 2 days. So the phases of the moon that we see, when viewed from above the North Pole, the moon orbits the Earth in a counterclockwise eastward direction, same direction the Earth is rotating. And the relative positions of the sun, Earth, and moon constantly change. And this causes different portions of the moon to be illuminated. Same side is always facing us, but the side of the moon that's facing the sun changes, and that's what's lit up. And the lunar phases are a consequence of the motion of the moon and the sunlight that's reflected from its surface. So here is a short video about the phases of the moon.
Hello, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe how and why the moon changes phases. When we look up in the night sky and we see something like this, what are we to make of it? What does it mean that the moon has this sort of crescent shape? Does this mean that the moon is actually a crescent and that somebody could, say, sit on that lower edge? Absolutely not. What you're looking at here is the moon as it always is, which is essentially a sphere, except different portions of the moon are lit up. And right now, in this picture, most of the moon is in shadow. But what's casting that shadow? A misconception that many students have is that that shadow is being cast by the Earth on the moon. That is absolutely not the case with the phases of the moon. That's the case with an eclipse. We talk about eclipses in a different portion of the textbook and in a different Smart Figure. So for the moment, set this aside. The phases of the moon have nothing to do with the Earth's shadow. Instead, what they have to do with is the moon's shadow. The moon is a solid object. It blocks light from the sun. And if you're looking at the shadow side of the moon, then the other side of the moon is the one that's lit by the sun. One problem here is the misnomer, the dark side of the moon. The dark side of the moon is dark for only half the time, and the side of the moon that faces Earth is dark for half the time. So really, the dark side of the moon should be called the far side of the moon. Anyhow, if you are standing on Earth and it's high noon and the sun's rays are coming directly down from above, then the moon, if it's directly above you at that point, will appear mostly in shadow. That'll be called the new moon, and it's illustrated down here. On the other hand, if the moon is moving into a position where we can see more and more of the sunlit portion of the moon, that is called a waxing moon. So if you're standing in this position here, basically at sunset, where the sun is setting to the west and the land to the east of you is already in shadow and darkness and night, then you will look up into the night sky and see the moon in this sort of a position here. So this is called a first quarter moon. And notice that the western half of the moon is lit because that's where the sun is, in the west. As more and more of the moon is flooded by light over the course of the month, we say it is waxing. It's growing in terms of the amount of the sunlit portion. When it's more sunlit than not, we call it a gibbous moon. Eventually, it gets to be on the opposite side of the planet from the sun, and so we can see pretty much all of its surface lit by the sun's rays. That's called a full moon, and that's going to be best viewed at night. If you're on the opposite side of the planet during a full moon, you're not going to be able to see it because it's not going to be in the sky. When we rotate around to this position here, we can see that we're at sunrise, where the land to the east of us is sunlit and the land to the west of us is still dark in night. And if we look up in the night sky, we're going to see, again, a gibbous or a third quarter or a crescent moon. But in this case, it's not waxing, it's waning. So more and more of the moon's surface is getting shadowed as opposed to being lit by the sun. And notice also that it is now the eastern half of the moon that's being lit. Here's a comparison of how that would look in the night sky. If you're looking at the same position over time, you would see basically that during sunrise, the eastern half of the moon would be lit, and so therefore this would be waning. And during sunset, if you see the western half of the moon lit, that's an indication that the phase of the moon is waxing. So that's a waxing crescent moon. Okay, let's go ahead and test out your knowledge here. Here we're looking down on Earth from above the North Pole, and the orbit of the moon is traced out with this circle. The incoming rays of light from the sun are shown by the yellow arrows on the right. Where would this phase of the moon fit in on this circle? Assume that the left side of the picture is east and the right side of the picture is west. So what you're looking at here is that the eastern half is lit and the moon is about half lit, so that's going to be a third quarter moon, and it's going to fit in somewhere about right here. What about this one? Well, that's obviously a full moon, so that's a pretty easy one. That's going to fit in over here, where the sunlit portion of the moon is the one that we can see from Earth's surface. How about this one? This is a crescent moon, and again, assume the eastern half is lit, so that makes it fit in about right here. And finally, we have a gibbous moon, which has the eastern half lit, so that's going to fit in about right here. Okay, I hope you got those right. Thanks a lot for your attention. This has been another Smart Figure.
So, for the phases of the moon from the Earth, it appears each day that the moon rises in the east and sets in the west, much like the sun. And it will change its relative position in the sky to the sun through its phases. At the full moon, it's going to be as far from the sun as it can be. At the new moon, as it gets closer to the new moon, it'll get closer to the sun. Now, the moon phases, its periodic change in appearance is its most outstanding visual feature. So one half of the moon is always reflecting light from the sun because it's the side of the moon that's facing the sun. But only when that side is all... But only when that illuminated side is the side that is also facing the Earth, that's a full moon. And when the illuminated side is facing away from the Earth, that's a new moon, and that's taken as the starting point for the month. It's arbitrary, but that's the standard. Excuse me. So the new phase or new moon occurs when the Earth, moon, sun, and moon are all in the same plane, and the moon is positioned between the sun and the Earth. So the dark side of the moon is the side that is faced towards the Earth. So this is the dark of the moon. you don't actually see the moon, you see the moon blocking things behind it. Now, the lunar phase vocabulary, there's the waxing phase, is when the illuminated portion is getting larger. This is from the new moon to the full moon. The waning phase is when the illuminated portion is getting smaller. Crescent moon is when less than half of the visible portion of the moon is illuminated. A gibbous moon is when more than half of the visible portion of the moon is illuminated. So starting at the new moon, you have waxing crescent, first quarter, waning crescent. Waxing. So new moon, waxing crescent, first quarter, waxing gibbous, full moon, waning gibbous, third quarter, waning crescent, back to new moon. So new, waxing crescent, first quarter. It's first quarter because it's the first quarter of the way around the moon, around the orbit for the moon, first, quarter of the month. Waxing gibbous, full moon. And during the waxing moon, the illuminated side is on the western side of the moon. Gibbous. And then during the waning moon, the illuminated side is on the eastern side of the moon. So you have full moon, then you have waning gibbous, last quarter, crescent. And people draw the moon wrong all the time. There's an excellent video from Minute Physics. I think it was Minute Physics. It might just be Henry Reich. Complaining, going over all the ways that people screw up drawing the moon out there, if you want to see that. So here is a video on the phases of the moon. So this observer is looking south, so the east is on the left. It's always the eastern side that's, east and west are correct in this, but in this image, if you're looking south, so east will be on your left. If you're in the southern hemisphere, you'll be looking north, so east will be on your right. But it will still be the eastern half that is dark during waxing and that is illuminated during waning. Come on.
For centuries, man has been intrigued by the moon's changing face. Sometimes it's high in the sky. Some nights it's a sliver. And other times, it disappears completely. But this cycle becomes predictable as the moon's phases repeat every month. The Sumerians, Chinese, and Babylonians depended on the moon's cycle to determine their days, months, and years. And the moon's phases still mark the beginnings of Jewish and Muslim holidays. So what causes the moon to have phases? And why is its cycle consistent? Phases represent the illuminated portion of the moon that we see from Earth. As the moon begins to orbit Earth, the sun's light reflects off the moon, causing a different portion to glow. The moon has 4 main phases. New, first quarter, full, and last quarter. It takes about 1 week for the moon to change from one of these phases to another. In between, the moon is either a crescent, which means it's less than half full, or gibbous, which is more than half full. When the moon appears to be growing, we say that it is waxing. If it appears to be getting smaller, it is waning. During a full moon, if the moon, Earth, and Sun align, and the moon passes through the Earth's shadow, a lunar eclipse will occur. But since the moon's orbit is inclined about 5 degrees to Earth's, the moon normally passes either above or below the Earth. The best time to observe the moon is during its quarter phases, because the terminator, which is the line that separates light from dark, dramatizes the moon's surface features. You'll be able to see mountains, craters, and scarps in the most contrast and sharpest relief.
Okay. So these are the phases of the moon. This is a lunar eclipse. This would actually occur during a new moon. This would be waxing gibbous, first quarter. Waxing crescent, first quarter, waxing gibbous, full, waning gibbous, third quarter, waning crescent. Assuming these are shot from the northern hemisphere. So a full moon will always be on the opposite side of the Earth from the sun. So when the sun is at its lowest position, the winter solstice, the moon will be at its highest. And due to the 5-degree difference between the Earth's and moon's orbital planes, the moon can be situated directly over the 28.5-degree north latitude line on the winter solstice. Let's see. So let's talk a little about eclipses. So the sun provides light for our solar system. And planets and moons within the solar system cast shadows that extend away from the sun. And the size and shape of the shadow that's cast depends on the object's size, shape, and distance from the sun. So the Earth and the moon will cast conical shadows as viewed from space, and an eclipse is the darkening of the light of one celestial body by another. So the shadows cast by the Earth and the moon cast 2 different degrees of darkness. There's the umbra, which is the darkest and smallest region. That's where a total eclipse occurs. And the penumbra, it's the semi-dark region where a partial eclipse occurs. So here's a short video about the difference between umbra and penumbra. Why are you not? Come on.
Earth. This shadow consists of 2 parts, the umbra and the penumbra. The umbra is a total shadow. To observers on Earth within the narrow strip of land over which the umbra passes, the sun appears to be completely covered by the moon. Those observers see a total eclipse. The penumbra is a partial shadow. To observers on Earth who are within the penumbra, the sun appears to be partially covered by the moon, so those observers see a partial eclipse. The Earth revolves around the sun in a slightly elliptical orbit. As the Earth orbits, its distance from the sun changes slightly during the year, causing a change in the apparent size of the sun to observers on Earth. The moon revolves around the Earth in a slightly elliptical orbit as well, which makes the appearance of the moon change somewhat during the course of a month. When the Earth is at its nearest distance to the sun, and when the moon is at its farthest distance from the Earth, observers within the moon's umbra see a ring of sun around it. This phenomenon is called an annular eclipse.
So eclipses are just shadows from various planets onto, from various objects onto other objects in space. And the fact that they were simply a shadow effects was first understood by the early Greeks. There are two types of eclipses. There is a solar eclipse, when the shadow of the moon falls on the Earth, so the moon blocks out the sun. When the moon moves in line directly between the Earth and the sun, this can only occur during a new moon phase. And the area affected by a solar eclipse on Earth is quite small, because the shadow of the moon only covers a very small point. There was an impressive one just a couple of years, last year, that came very close to us, but yeah. So a solar eclipse is when the shadow of the moon falls on the Earth. So only a limited area gets affected. There are about 2 solar eclipses a year, but where they can be seen varies. So like, I think the most recent solar eclipse was in the Pacific Ocean or something. You can look it up. There's Wikipedia has all the eclipses for the next, couple hundred years. So here's a video showing, the shadow of the moon on the Earth, and you can see how the shadow of the moon, there's this larger area where the sun is partially blocked, and the small area in the center where the sun is completely blocked, and that's the eclipse. And you just see a total eclipse if you're in the area that little dot passes over, and a partial eclipse in the larger area. Again, this shadow passes over. See the little dot, that's where a total eclipse is observed. And the larger area, you see a partial eclipse. So again, a solar eclipse occurs when the moon blocks some or all of the sun's rays from an observer on Earth. And it will occur when the sun is at or near new phase and is in or near the ecliptic plane. And when the moon lies between the sun and the Earth in nearly a straight line, the shadow of the moon will fall on the Earth. So this can really only happen about twice a year, when the orbits of the Earth and the moon line up properly. And the umbra and the penumbra are the dark and semi-dark shadows cast on the Earth by the moon. So that umbra and penumbra are just terms for any shadow. There's the darkest part of the shadow and the partially shadowed portion. So all shadows have an umbra and a penumbra. They're more relevant for eclipses because they're really dramatic shadow effects, but your shadow has an umbra and a penumbra, but the difference is quite small for your shadow compared to the shadow of the moon on the Earth, for example. And the length of the moon's shadow varies with the moon's distance from the sun. So in some cases, the moon's umbra doesn't reach all the way to Earth, and you get what's called an annular eclipse. And there was one of those passing through the US just recently as well. And the maximum diameter of the umbra on Earth is about 270 kilometers, and a total eclipse is when the umbra reaches Earth. So here is a short video on solar eclipses.
A solar eclipse happens when a new moon moves between the Earth and the sun, blocking some or all of the sun's rays from reaching the Earth. By cosmic chance, even though the sun is 400 times wider than the moon, it's also 400 times farther away. Therefore, the two objects appear the same size in our sky. Astronomers are able to predict eclipses because the Earth and Moon have very predictable orbits.
Oops.
Why then isn't there an eclipse every month? The moon's orbit is usually tilted a few degrees north or south in relation to the Earth. When the moon does eclipse the sun, it casts two types of shadows on Earth: a smaller, darker shadow known as the umbra, and a larger shadow known as the penumbra. There are four types of solar eclipses. The first and most spectacular is a total eclipse, when the moon completely covers the sun's surface. A total eclipse can only be seen if you're standing within the umbral shadow. That's why the imaginary line created by this shadow as it races across Earth is known as the path of totality. People within the penumbral shadow see only a partial eclipse, the second type. From this view, outside the path of totality, the moon passes in front of the sun off-center, never fully covering its surface. Third, an annular eclipse occurs when the moon passes directly in front of the sun. However, unlike a total eclipse, the moon appears too small to fully cover the sun. The moon's orbit is elliptical, so sometimes it's closer to Earth and sometimes it's farther away. Last, a hybrid eclipse is when the moon's position between the Earth and sun is so finely balanced that the curvature of the Earth plays a role. The moon will be farther away from some parts of Earth along the eclipse's path, resulting in an annular eclipse. In other parts, the moon will be just close enough to fully cover the sun, resulting in a total eclipse. While a total solar eclipse happens somewhere on Earth every year or two, any given point on Earth experiences the event only about once every 400 years. We interrupt this video for an important safety announcement. Looking directly at the sun, even during an eclipse, can cause permanent eye damage. Fortunately, there are ways to enjoy an eclipse safely. The easiest is to use certified eclipse-watching glasses, which are shaded thousands of times darker than typical sunglasses. You can also look at the eclipse indirectly by making a pinhole viewer. Simply poke a small hole in a piece of cardboard. Hold the cardboard up to the sun, allowing the sun's image to be projected onto a flat surface. Be sure to look only at the surface and not through the cardboard. Just before the moon completely covers the sun, low-lying valleys on the moon's edge will be the only spots that sunlight continues to pass through. These remaining brilliant shafts of light, known as Bailey's beads, will disappear one after another. And finally, a single bead of light remains, known as the diamond ring, signaling that you're just seconds away from experiencing totality. Once the last bead disappears and the moon completely covers the sun's surface, the view through your eclipse glasses will be pitch black. Totality achieved. At this point, none of the sun's rays are reaching your eyes, and it's the only time that it's safe to take off your glasses. Remember to put your eclipse glasses back on before any of the sun's rays start to peek through again. Any sunlight reaching your eyes, even for a few seconds, can cause serious damage. While an eclipse can last a few hours, totality typically occurs for less than 3 minutes. Animals and plants have also been known to alter their behavior during a total eclipse. Songbirds may stop singing, crickets may start chirping, and flowers may even start to close up. We won't always be able to see total solar eclipses. The moon moves about 1.5 inches away from Earth each year. It's estimated that in about 1 billion years, the moon will be too far away from Earth to completely cover the sun.
So this is solar eclipse. This is a total solar eclipse. This is an annular solar eclipse. Before we let you go, I have a quick video that I'd like to show you. This is an animation, another animation of the formation of the moon that's sort of showing that process of Mars-like object hits the Earth, splashes material out, some gets flung out, some falls back down, and some condenses to form the moon. Very violent and chaotic. And if you'd like to see what eclipses look like on other planets, Minute Labs has a thing where you can see what eclipses look like on various planets, and you can see why Earth has the best eclipses in the solar system. So and that planet that hit Earth has been named. It's Theia. Theia? But if you want to see what eclipses look like on other planets, Minute Labs. Eclipse Explorer. So here you can choose to see various eclipses. Here's Earth, but you can change to say Mars and Phobos or Deimos, for example. And you can see the eclipses of Phobos and Deimos are much less impressive because they are much smaller. But that is all for today. I'll see you on Wednesday. Weather was crazy. Have a nice day.
Professor, I have a
Yes.
question. Regarding the lab, since we don't have class, can I turn in the lab on Thursday?
On Wednesday, yes.
It's for next week?
So the lab that was due, so basically the lab that would have been today is just getting pushed back to next week. We're just going to delay all the labs. The lab that was due, the weather map lab, you can turn that in. Because I don't think I have the weather map lab from everybody.
The weather
It's the one we did a while ago.
Oh, okay. No, I already turned that in. Yeah, I was wondering.
But so I'm not, the lab that would have been today, we will do next week. We're not doing it today. You don't have to turn it in later this week. We're just going to shift all the labs back a week.
And then the weather mapping one, just give it to you on Wednesday.
Yeah, just get it in as soon as you can. If you haven't turned it in already.
All right, sounds good. Thank you.
Yeah. So, but for the labs, basically what we're doing is we're just, we would have been doing a lab today. We're just not doing it today. We'll do it next week. We have enough time, so we don't have to like panic about that. Especially because the last lab is short and easy. So, but I looked at the schedule. There's enough space to do that.
And no lab today, right?
So no lab today.
Okay.
So just enjoy yourself. Okay.
All right, thank you. Bye.
See you all on Wednesday. I'm going to end.